Okay, coupling functions, very powerful. Remember that. So, stoichiometry. So this again is just a few definitions until we get to what's called the mixture fraction. Stoichiometric, of course, you all know this, is when fuel to oxygen ratio is such that both are entirely consumed when they are converted to CO2 and H2O. Now, of course, you realize this here is true if you have hydrocarbon fuels. Most of what we will talk about here is hydrocarbon fuels. So sometimes when you see these definitions, whatever, I always try to keep them not too general, because if you put a definition in very, very general terms, nobody understands it, but it will be right. So I try to maybe sometimes be not so general so you understand it, but you have to see that it makes certain assumptions. So that's the case here also. Global reaction here, for example, I wrote you here the methane global reaction. That would be, so if you have 1 mole of methane plus 2 moles of oxygen, that would be stoichiometric. So the mole number ratio for stoichiometric condition here is NO2 divided by N fuel, or nu O2 divided by nu fuel. That's the same. So you get these ratios here. You can get these always from the global reaction. And now I can write this in terms of mass also by just multiplying this here by the molecular weights. And then we get this, what we call it the stoichiometric mass ratio. That's an important quantity also. Nu is the is the stoichiometric mass ratio, or the mass ratio in which these oxygen fuel would be in stoichiometric proportions. Typical value, look at the example here, methane combustion, nu O2 divided by nu F would be 2 here, and then the molecular weight of oxygen molecule is 32, methane is 16, is another factor of 2, so it's 4. So typical value for methane is 4. Just, if one keeps that in mind. We'll see later on if that's helpful. So if the mass ratio of oxidizer and fuel is equal to this nu value, here maybe 4, then both are consumed when combustion is completed. Okay, so this could have been observed also from the coupling function. Take this coupling function here and multiply here with nu O2 times WO2. Then you get this new factor in here, the stoichiometric mass ratio. And now for stoichiometric combustion, you want that oxygen and fuel both completely, fuel and oxygen both completely disappear. So YF and YO2 are 0. And then you see that YO2 over YF should be is new again. So this could have been just observed from the coupling function, of course. Okay, so these are just a few more definitions. You see it's green. I'll skip these because we don't need these. So this minimum oxygen, minimum air requirement. I'll just skip these. So then we can define the equivalence ratio. The equivalence ratio is known to all of you. The equivalence ratio is, in a sense, it's a really smart definition. It is the ratio, let's say the mass ratio of fuel to oxygen, divided by what the mass ratio that you would have for stoichiometric conditions. Okay? So if the equivalence ratio is 1, this is exactly stoichiometric conditions. If it's larger than 1, you have more fuel. Smaller than 1, you have more air. And you see that here in the denominator, you have the mass ratio, the stoichiometric mass ratio, which is nu, so you can just write it like this. This can be, and the reason why I'm saying it's a very smart way of defining a quantity like this, is because you can write, because it always normalized with a stoichiometric stoichiometric ratio, so you can write it in many different forms. You can write this. What does that mean? can be written in terms of fuel to air ratio. I don't know what this means. But it can be written also in terms of mole fractions. Okay? So if you just replace every single x by a y, every single y by an x, you know, then it's true, it's correct also. Okay? So it's a good quantity. So this is you can write in many different ways, but this is the typical form to use where nu here is just obtained from the global reaction, as we saw earlier, the stoichiometric mass ratio, and then mass fractions is typically what we are concerned with. So equivalence ratio, everyone knows this. Maybe most of you know mixture fraction also, but mixture fraction is a really, really important quantity. So we want to introduce this real quick. So mixture fraction is one more thing. I mean, this first lecture, many things, so I see everyone is looking for the slide. I always do this. Last second, I look at the slides and I don't like this and I make changes and so on. So here in this part, I've made a few changes. I don't think anything is wrong what you have, but I just reorganized it a little bit. So you'll find all of this maybe just in a different order. And maybe one or two things I just added. So the equivalence ratio we know is very, very important in combustion. If you have a rich mixture, you burn it, you get lots of pollutants and whatnot. You get CO emissions bad. If things are too lean, then they don't burn anymore. There's a flammability limit and things like this. So equivalence ratio is very, very important. We use the equivalence ratio mostly in premixed combustion. We don't use it very much in non-premixed combustion. In non-premixed combustion, we define a different quantity, which in fact is exactly the same as the equivalence ratio. It's just defined in a slightly different way. So it's a little more useful. We'll see at the end why it's more useful than the equivalence ratio. So that's the mixture fraction. The mixture fraction quantifies just a local fuel-to-air ratio, and we use it for non-premixed combustion. So consider two separate streams. One is a fuel stream, one the oxidizer stream. It's just like this little burner we looked at in the beginning. And then these streams, they mix and they burn. And so fuel here, you know, could consist of only one component. In general, it does not contain oxidizer, but it could. Oxidizer stream, in general, it does not contain fuel, but it could. So the point here is not so mixture fraction, it doesn't really look so much at how much fuel you mix with how much air. It looks more at you have two streams. How much stream 1 do you mix with stream 2? Now, it could be that stream 1 is pure fuel and the other one is pure air, but they could be anything. You just know at the end of the day, I have so much from this stream and I have so much from that stream. Okay? So, if we say the fuel, so we call one the fuel stream and the other one the oxidizer stream. The fuel stream, we always use here subscript 1. The oxidizer stream, always subscript 2. And then we define the mixture fraction like this. The mixture fraction is, so take this thing here, and now I define a little volume here, somewhere downstream of this. Let's say I have this burn, or I have it not burn. I could just open this. Now I mix propane with air. I take a little volume and I measure how much propane I have and how much air I have, okay? So this here is just in this little volume, it's the mass of propane, or more generally, the mass originating from the fuel, okay? It could already be CO2, but then I would count only the carbon because that's the mass that's originating from the fuel. So the mass originating from the fuel divided by the total mass originated from both streams. Okay, so that's how it's defined. You see easily either have no mass of the fuel, then mixture fraction is 0, or it's pure fuel, then mixture fraction is 1. So it varies between 0 and 1. That's a good advantage. See here, I noted this. Index B means fuel. So if I now in these two streams, I have fuel and oxidizer. In the fuel stream, I have a certain mass of fuel, mass fraction of fuel. We call this Y fuel in stream 1, and I have in the oxidizer stream, I have a certain mass of oxygen, Y oxidizer 2. For this here, we make the assumption there's no fuel in the oxidizer and there's no oxidizer in the fuel stream. And then we can you try to derive mixture fraction from the definition in terms of these mass fractions. For that, we can start out with this relation here. This just says in any volume, this volume I just showed you, I have a mass of fuel, and that's nothing else than the mass in this volume I had from stream 1 times the mass fraction of fuel in that stream 1, if, let's say, the fuel is mixed with nitrogen or whatever. And then if I divide this here by the total mass, I get this. Divide this by total mass, this would be mass fraction of fuel. YB1 remains, and then this here will be M1 divided by the total mass. That is the mixture fraction. I can do the same thing here for the oxidizer, and I have these two relations here, which are true as long as nothing burned. This is in the unburned, okay? And now I can also use the coupling function. I go back, use the coupling function. I just put these relations in here, and then I can solve this for mixture fraction, and I get this. So this is the definition of mixture fraction in terms of mass fraction O2 and mass fraction fuel. Yes?
So for a premix, the mixture fraction would be the mass fraction of the fuel in the premixture?
So you're talking about now a totally premixed system. Yes. For the totally so let's take a box, and the box is filled with a fuel-air mixture. Then this whole definition doesn't make so much sense, because I said in the beginning we have two streams. Now you could say, take the box is empty, a vacuum, and I have two streams. I fill it with some mass from oxidizer and some mass fuel. Okay? Now I have two streams again, and I can do the same thing. I can just define what mass came from this stream, what mass came from that stream. If I say this was a pure fuel stream, pure oxidizer stream, then you see here that this YB1, that would be equal to 1, because the mass fraction in the fuel stream is equal to 1. And then, is the same thing. If it was a pure oxygen stream, then this would be 1. A pure fuel stream, then this would be 1 also. Okay? So you can do it just like this. It just doesn't make so much sense, because here really we're looking at two different streams. Thanks for the question, though. I want to encourage you to ask questions in between. If you ask a question, you think maybe you don't want to ask a question because you think it's a stupid question. Most of your peers here also don't know the answer to that question. There's a very good chance you will help others also to understand that same point. Also in the breaks, feel free to come and talk. I just in the break want to get a coffee real quick, and then if you have questions, we can discuss these in the breaks. Okay, good. So this mixture fraction, this is a very, very interesting quantity, because it comes out of the coupling function. It really, this is just definition here, but it comes out of the coupling function. This is the underlying relation here, which means it is a conserved quantity, this mixture fraction, because it looks at the mass that originated, from the fuel. It doesn't change during combustion. So take that example. You take the little box. You fill it with two different streams. I just measure the mass I have from each stream. Now it's pre-mixed, and I have a certain value of mixture fraction. Let's say 0.5. And now I burn whatever's in the box, and afterwards it's still 0.5. Okay, it doesn't change during combustion. Now, that's interesting, because this looks like it would change during combustion, because during combustion YB changes, but also YO2 changes. And the way they change is through the coupling function, such that this sum, nu times YB minus YO2, they don't change. Okay? So you, you know, this is where the coupling function comes in. Okay. Good. So, definition of the mixture fraction. Now you can look at a stoichiometric composition. Stoichiometric means at stoichiometric, once it's burned, YB and YO2 should be 0. So we just set this here equal to 0. And so this is the stoichiometric value. Now we can think of what's the stoichiometric, typical stoichiometric value. Let's burn methane, pure methane, with pure oxygen. Okay? Then, as I said earlier, this YO22, that would be the mass fraction of oxygen in the oxidizer stream. That is now equal to 1. This is equal to 1. This is equal to 1. So this 1 divided by this was 4. 1 divided by 5 is 0.2. 0.2, that's burning methane with pure oxygen. What happens if you burn methane with pure air? Then YO2, the mass fraction of oxygen in air, is roughly 0.233 or something like that, 0.23. Okay? So let's say it's 0.25. It's easier. If this is 0.25, this is 4 times 1, 4, plus 4.25, so it's 0.25 divided by 4.25, multiply this by 4 is 1 divided by 17, 1/17. Okay? So that's about 0.55 or 0.58 or something. 0.055. Okay? So stoichiometric mixture fraction for methane in air is about 0.055. Okay? So stoichiometric means equivalence ratio is 1, and now you see the stoichiometric value for mixture fraction, it always depends on exactly what you have in your streams and so on, but fuel with air, it would be 0.055. So it's relatively small. I mean, typically, it is very small. Okay, so this is how I can write this if I want to write it differently, but that's what it is. Okay, there are different definitions. You see that here, because we used the coupling function. The coupling function here was derived with a one-step global reaction. Fuel plus oxygen goes to products. Fuel plus oxygen goes to products. You know, that's an assumption that's usually not true. I mean, it's things are more complicated in real life than that. And so there's another definition here that is just based on counting the elements. As I said earlier, the elements are conserved, so from that also we can derive a coupling function. So this is how you do this. Consider CHO as elements here in a fuel, CMHN that burns with oxygen or air. Then this is how a global reaction would look like. This is combustion of a hydrocarbon fuel. So now again, we can write these coupling functions. Earlier we wrote here this thing that just tells you how often does a reaction take place. Now we can measure how much, so in a certain time, let's say, how many carbon did we consume, okay? And so how many carbon we consume divided then by the number of carbon in this fuel, that would give us the number of fuel molecules we consumed, and then we are back to this thing here really divided by the stoichiometric coefficient. That tells you how often did the reaction happen. I can write this for C, H, and O, and you see all three should be the same. I can also write this then, so this is in terms of the number or the moles. This is in terms of element mass fractions, and then so if all of these are same, I can say I can take this plus this minus 2 of these, okay, and that should be 0, or you could say, so that should be 0, which means the change, so if I define a quantity beta here like this, then this has a certain value, whatever the value is. I can compute this value, but a change, so combustion should not change this value, okay? Because is defined such that the change is 0. These shouldn't change anyways, but it's defined to change in stoichiometric proportions. Okay, so now I have this so this is a coupling function beta. I can define the mixture fraction now again, based on this beta. I just want to define it such again that it's 0 in the oxidizer stream and 1 in the fuel stream. So I can just define it as mixture fraction is beta minus the beta value in the pure oxidizer stream divided by the values of beta in the fuel stream minus that of the oxidizer stream. Okay, so these beta 1, beta 2, they just depend on the composition of these streams. But then I can plug it all in, and I get something like this. And you see that looks very similar to what we had earlier, but now it's all based on these element mass fractions. And the element mass fractions, again, we saw this earlier in this lecture, they can be related back to the mass fractions. So I can also replace these element mass fractions by the actual mass fractions if I want, but then I have these this matrix here in the definition. So that's just a different definition of mixture fraction that doesn't make the assumption of one-step global reaction. This is a definition here that's introduced by Bob Bilger. This also can be nicely used to look at experimental data, because experimental data you have maybe so the one-step reaction, it would say methane plus oxygen goes to CO2, but maybe you do measurement and you find CO in your measurement and all these things, and then you can evaluate the mixture fraction, based on all the measurements you did. Okay, there are other definitions also. We have our own definition, which I won't tell you now, which is yet different. And I wrote a paper on this some time back, discussing the different features of some of these mixture fractions. Okay, so now we can look at the relation between mixture fraction and equivalence ratio. This was the equivalence definition of equivalence ratio. They have something to do with each other. I mentioned this earlier. And then if I introduce these relations here again into this definition, if I introduce this in the coupling function, then this leads to this here, where you see I have this here is related to the equivalence ratio, and I can derive this relation, which says the equivalence ratio is nothing else than mixture fraction divided by 1 minus mixture fraction times 1 minus z stoichiometric over z stoichiometric. Okay? So what this shows you is, first of all, this gives you a relation how you can convert one to the other. But secondly, it shows you that these are uniquely related. Okay? You could say it's exactly the same. It's this different value, but the physical meaning is exactly the same. A lot of students have problems visualizing mixture fraction. Most of the students have no problem visualizing equivalence ratio. So just think of mixture fraction as the same as equivalence ratio. So if it is the same, why again do we introduce a new quantity again? Okay, if I tell you it is the same, why do we need to introduce it?
Is it because Z is bounded, but Q isn't bounded?
Exactly. So if you think of non-premixed combustion, then I turn this thing on here again. I have pure fuel in the center. Pure fuel in terms of equivalence ratio means infinity. If I want to write an equation for this, it's never good. Infinity in an equation is never good. So basically you can think of mixture fraction just as the same as equivalence ratio, just normalized back to vary between 0 and 1. Okay? Equivalence ratio varies between 0 and infinity. Stoichiometric is 1. Mixture fraction varies between 0 and 1. Stoichiometric would be z stoichiometric. Okay? Phi equal to 0 is the same as z equal to 0. Okay, that's simple. So in a sense, they go in the same direction. Just one is scaled back to vary between 0 and 1. Okay. Yes?
How would this look with like methane and air and the presence of combustion products as well? Like, are the combustion products included in the calculation?
Yes, they are all included in the calculation. That's what I said earlier here. So if you look at this here, for example, so we didn't make the assumption here that it doesn't burn. We just introduced, this is a true relation. If it's unburned, then this holds. If it is unburned, then this holds. But the coupling function, it relates unburned to burnt, okay? And so we just replaced these values here, the unburned values, we replaced this by mixture fraction. The unburned values here, they could be written in terms of equivalence ratio. But we replace them by mixture fraction, and then we get this, which means these here are the values in the flame, you know? I mean, they could be, as a matter of fact, if you measure these exactly at stoichiometric conditions, then these here should be 0, and then you get the stoichiometric value, you should get this, which then tells you, okay, go back to this here. If I measure the stoichiometric value, you see then, z equal to z stoichiometric, you see phi is equal to 1. Okay? So this is all consistent. The only issue is that if you take, we talked about heptane before. Heptane, if you burn heptane, or even propane, if you burn heptane, heptane will be converted to, in the rich part of the flame, it will be converted to ethylene, C2H4. That in a thin layer. Then the ethylene will be converted to maybe acetylene. The acetylene will be converted to CO, and the CO will be converted to CO2. Okay. So if you do a measurement, then you will find a place where you have no fuel, no oxygen, but it's not stoichiometric. You have a lot of intermediates, and so the one-step global reaction, it doesn't always work. I mean, if you want to, it works conceptually very well, but if you want to evaluate your experiments, then you might have to use this other formulation here. Sorry, this bigger-based formulation here. But that has issues also, because here also we assume there's no differential diffusion, and once you have differential diffusion, then you know things become funny again. Yes.
Is there a quantity for a three-stream?
Yes, you could use 2 mixture fractions. 3-stream, you would use 2 mixture fractions. Yeah, that's we do that as a matter of fact, because sometimes you have 3-stream problems, but it gets a little complicated. Yeah, it's not so easy. Okay. Good. We talked about this. So this also holds for multi-component fuels. It also holds for, you know, if you have air in the fuel and all of this, and it can be derived easily. And there's an exercise here. This shows this, which we. So there's no solution, just an exercise in case you want to look at this. Okay, so now from you know, looking at this, everything we said so far, we can also start looking at the structure of a flame. We want to look at the structure. How does a diffusion flame look like in terms of this mixture fraction? And first of all, we can already say, let's say you have a lifted flame. Flame is lifted off the burner. Then you have just mixing of fuel and air before the flame starts burning, okay? Or if I just open this up before igniting, I just have mixing. Now, mixing can be expressed just by these functions here we had earlier, where we say, okay, now this is the solution. This is exactly the solution we get here, but not as function of space. This is the solution as function of the mixture fraction, okay? Where mixture fraction 0, that's pure air. So this here would be 0.23 in our case. And then the oxygen concentration or oxygen mass fraction varies linearly with mixture fraction. And in the pure fuel, it's 0. And fuel here, now in our case here, this would be equal to 1, because you know, it's pure propane that's coming out here. That varies linearly with mixture fraction again. Okay? So this is what happens before we ignite the flame, or maybe, you know, in the lifted flame before you reach the actual flame. Now we want to look at what happens if it burns. And we can use these relations also to find what happens when it burns. We said earlier stoichiometric composition means stoichiometric proportions is this here. Now if mixture fraction is smaller than stoichiometric, then you have more air or more oxygen than you have fuel in terms of the stoichiometric balance. And so the fuel will be all, smaller than stoichiometric, the fuel will be all consumed and there's oxygen left. And so combustion terminates here when all the fuel is gone. If we now assume that we have fast reaction, complete conversion to CO2 and H2O, then we can start here with this, and we can say now YF is equal to 0 in the lean, okay? And then you see this gives us a relation between mixture fraction and O2 mass fraction. So you can just solve this for YO2, and then this is what you get. This is the solution now for Z smaller than stoichiometric, and you see that O2 again varies linearly even when it burns, linearly with mixture fraction, and also you see it goes to 0 at stoichiometric. Z is equal to stoichiometric, then this will be 0. Okay. Now we can do in the rich, oxygen should be 0. We can you do the same thing. Take this relation, set oxygen to 0. This will give you a relation between fuel and mass fraction, as written here, and then so this is fuel and air or fuel and oxygen. Now we can also try to look at CO2 and H2O, let's say. Now for that, these don't appear. They don't appear here in this thing. But again, what we know is that the element mass fractions, they don't change. Okay? So if we have a certain mass fraction of carbon, because we have a certain amount of fuel, then all that fuel will be converted, I mean, if we make that assumption, will be converted to CO2, and you see already that this tells me then, gives me a relation for how to compute CO2. So that's what we do here. So these are the relations we had earlier. These are the element mass fractions of carbon, hydrogen, and oxygen atoms in the unburned, okay? But unburned fuel and unburned oxygen, we know we had these relations earlier. On the other side, once it burns, then I can just use the definition here of these element mass fractions. Element mass fraction, remember we had this earlier. Now, once it burned, I might have some carbon still in the fuel, and I might have some carbon here in CO2. Hydrogen, same thing. I might have some in the fuel. I might have some in the water. And then for oxygen, I might still have some in O2. I have some in CO2. I have some in hydrogen. And now what's interesting is that the element mass fractions, they don't change over combustion. They stay the same. I can equate this here with this. And you see it gives me a relation for CO2 in terms of YF burned and YFU. And I can solve this. I can replace YFU. I can replace this again by mixture fraction. Okay? And YF burned I can also replace by mixture fraction. And so this gives me these relations here. If you do this, you plug all these things in, you get these very simple or relatively simple relations here for CO2 and H2O. Again, both for these smaller and stoichiometric and larger stoichiometric, you get different relations. Okay, so this again, I mean, if you look at these relations, here you see the maximum is reached actually both solutions, of course, have to be equal at stoichiometric, and that's the maximum. And so this is kind of how it looks like. So if we look at combustion, or hydrocarbon, pure hydrocarbon with pure air, then you get a solution like this. As function of mixture fraction, you see that you get, and we assume infinitely fast chemistry and full conversion to products. Okay, if we do that under these assumptions, this is what we assumed in getting these relations, then this is how it looks like. You get the maximum here at stoichiometric. We actually have a value for this also. This is a quantitative value for these here. So you can really quantitatively, here stoichiometric value, you can quantitatively determine these. And oxygen here goes to 0 at stoichiometric and is 0 in the rich. Fuel goes linearly to 0 here and is 0 in the lean. Okay? This is the so-called Burke-Schumann solution. This is goes back to the 1920s or so. And it is what you get if you assume infinitely fast, irreversible chemistry. Okay? So you see that using the mixture fraction not only has the advantage that you scale it back between 0 and 1, it also is defined in a very smart way, as you see. It's defined such that you get these nice linear relationships. Linear because we use the coupling function to define it. We didn't just say, let's scale this back to something that varies between 0 and 1. We derived it from the coupling function, and the coupling function just is linear with, it provides a linear relationship between all the different species. So what's missing here is one thing is still missing here. This is not the full solution. What's missing? One thing that is always of interest also, if you look at a combustion problem.
Equilibrium products at form as a result.
We'll hold that thought. We come back to this. Temperature. We don't know temperature yet. Okay? We'll do that next. Okay. Good. Then to summarize, so I put these basically table of contents here at the end as a summary. We introduced some just basic quantities, mass fraction and whatnot. We said that different quantities are important for different questions we ask. Mass fraction for this, mole fraction for that. We talked about elementary global reactions. We use global reactions very often here. You see in these to define these coupling functions. The coupling function just relate. So because a global reaction, it really ties the change, the chemical change of different species to each other, and the coupling function is just a quantitative representation of this. We use that here just to define a mixture fraction, but the coupling functions can also be used usually to reduce a system to a smaller size. Again, we'll see later on that here you see I can relate this, this, and this all to the change of this. But then you can imagine also, if I convert 1 mole of this with 2 moles of this, that leads to a certain temperature change. Okay, that leads to a given heat release. So I can also tie the temperature, I can also tie this with coupling functions back to the change of these species. So we'll see this later on. Talked about stoichiometry, and we talked about mixture fraction, which is the same as the equivalence ratio, just something that we use for non-premixed combustion where we have pure fuel and pure air, because pure fuel is because, yes, for pure fuel, equivalence ratio would be infinity and so on. The other reason why we use this is, now you can imagine, I just told you how the flame structure, the entire flame, under these assumptions, of course, but how the entire flame looks like as function of mixture fraction. Which means, if you could measure mixture fraction, let's say you could, then you just measure mixture fraction 1 point and you know everything. Okay? Now, it's really hard to measure mixture fraction because it's just a combination of different species and so on. You might as well measure all species, you don't need the mixture fraction anymore. But you can compute mixture fraction. I mentioned earlier, mixture fraction is a conserved quantity because derived from the coupling function. It's a conserved quantity. It does not change during combustion. If you write a differential equation for mixture fraction, it has no chemical source term. You can compute this very easily, no problem. Let's say you compute the fluid flow here in this thing, fluid flow in this thing, and you just solve one equation in addition to a momentum equation, continuity equation, you just solve one equation for mixture fraction. Then you have all the the mass fractions of fuel, product. We'll see in the next lecture. You get the temperature also. You don't need to do anything else. Okay, that is though with a grain of salt. This is infinitely fast, irreversible chemistry. That's sometimes not so bad. Actually, sometimes for certain things, is not a bad assumption. Okay, here you have your CFD already. If you want to do CFD tonight, code up conserved scalar equation, and you can do combustion in non-periodic systems already. Okay, good. So let's see. We come to the next thing. I always put this golden template here for you, so you can get back to good state of mind. So how are we doing with time? We are supposed to have the next break at 11. Yes. Good. So let's see if we can do some work before that. So now we want to talk about thermodynamics. You'll see here a lot of this is boring. Again, I mean, it's just a lot of definitions. I'll go over these definitions quickly. There's one thing missing here, I guess. I go over these definitions quickly and, just point out what's important. So there are three things that we want to talk about here, I think, right? Definition, thermodynamic quantities, just definitions. The definitions you have seen before. There's some things that are important for combustion, and we want to highlight these. Then we'll talk about first law of thermodynamics. This would be flame temperature at complete conversion. Okay, or the application of the first law of thermodynamics will give us the flame temperature. And then we'll talk about the second law of thermodynamics. That will tell us something about chemical equilibrium, which is, again, the composition you will have if you wait 10 trillion years or whatever. That's but sometimes when temperatures are high, equilibrium is reached much, much faster, and then you don't need to wait that long. Okay, good. So that's what we want to do. Start out with this. U is the internal energy. This is a change in internal energy. The work here is PdV or minus PdV. V is the specific volume, is 1 over the density. Here, of course, we usually deal with the density. dQ is a small amount of heat transfer or heat, and we can write the first law of thermodynamics in terms of these quantities written down here. It's very simple. du is dq plus dw, and that's it. This here would be the reversible work. So for a reversible work process, this would be the first law. Enthalpy is U plus PV. For an ideal gas, now this is interesting already, PV can be written as RT over W, which means for an ideal gas, U is a function of temperature only. Most of you might remember this. It's not a function of pressure. Enthalpy, because of this relation here, is also just a function of temperature. U is a function of temperature. Here's the temperature. So both enthalpy and internal energy are function only of the temperature for an ideal gas. Okay, so that's what we are usually concerned with. Entropy, come to this later, of course depends on the pressure also. So now we talk about mixtures of gases. We can write the internal energy here as the internal energy of an individual species times the mass fraction summed as over all species. Same here for the enthalpy. The enthalpy here, or the internal energy of individual species, they now depend only on temperature. It can be written like this. The enthalpy here is we usually deal with enthalpy, and you'll see later on why. Or of course you know why. When do you, in thermodynamics, when do you use internal energy? When do you use enthalpy? Right, so constant pressure, constant volume. Constant pressure means enthalpy is a good thing to use. You can also use internal energy, it's not wrong, it's just things are more complicated. Enthalpy is a very convenient quantity to use when you have a constant pressure process. A lot of combustion processes are constant pressure. For example, this burner here, you know, I burn here at constant pressure. A gas turbine burns at constant pressure. Internal combustion engines, they burn not at constant pressure, maybe not even at constant volume, but is a closed system. And so typically people look at maybe internal energy. You know, when you talk about internal combustion engines, or when you talk about a homogeneous reactor, very often or shock tubes, we think of constant volume, but let's say most or many combustion processes are constant pressure, which is why enthalpy is interesting. So this is how the enthalpy is defined. This is a very, very important relation. Of course, you know the enthalpy has two contributions. In your typical thermodynamics course, you would only talk about the second one. That's perfectly fine. This is the sensible enthalpy. Sensible enthalpy, you change the temperature, you change the energy, you know, amount of energy you have, and you change the enthalpy. That's what this is. Depends here, so we have an equation of state, which involves here the heat capacity or specific heat of that species, which again is a temperature function. And so I can integrate this and I get what's called the sensible enthalpy. When we talk about combustion, this other part here is very important. You see this here is just, this is the enthalpy. The sensible enthalpy is just a change of the enthalpy if I heat something up from a reference temperature to another temperature. And for many questions, that's important. That's just enough. For combustion, it's not enough. For combustion, we need to consider that at the reference condition, we have a certain enthalpy also. That is it's called enthalpy of formation. So if you think of a fuel, let's say, being put together by elements. You have carbon and you have hydrogen. Then these carbon and hydrogen, they have certain enthalpy. And when you put these together, you change the enthalpy of the system. And that enthalpy is the enthalpy of formation. Okay? It's defined also with respect, again, to some other, maybe to the, you could say maybe to the enthalpy of the elements. Okay? But that's the enthalpy of formation. Now, when we do combustion, this part of the enthalpy is very, very important. Why? Because when we do combustion, we do nothing else than moving enthalpy from this part to that part. We'll see later on, over combustion process, here, typical combustion process, the enthalpy is this, it doesn't change. Okay? It doesn't change. But what we do is, we move enthalpy from here to here, which means in the beginning we have oxygen and we have fuel. We have a very large energy in the chemical energy in the fuel. The chemical energy in the fuel, or I say chemical energy in the fuel, really should say we have a potential because we have, you know, this oxygen and the fuel together, they have a potential to do something else, and so that gives you a high energy, but or you could think of it as a potential energy with respect to the products or whatever. But we have a high chemical energy here in the fuel and the oxygen. Okay? And once we convert these to CO2 and H2O, then the chemical energy in these is very, very low. Okay? So what we did is we moved the chemical energy from here to here. If we have a lot of energy in this part or enthalpy in this part, it just means we increase the temperature. That's what we do. We move, I mean, of course, you know this. When we burn stuff, we convert chemical energy into thermal energy. And that is what you see in this relation. That's expressed in this relation. You move energy from the first term to the second term. So this first term here is very important for us. Typically, this is defined at a reference. You could do 0 Kelvin, but usually in the tables you find, I think, usually it's with respect, the reference temperature is 298.15. Right, so this is just different forms here. So this here was specific enthalpy, which means the mass-based enthalpy. This here is just the same in terms of the molar enthalpy. We don't need to go through this. This is the heat, specific heat here, which also can be related to the specific heats of the individual component. This is the mixture specific heat. Okay, so I said earlier the reference enthalpy, or the enthalpy of formation, is that's listed in tables also. But that again has to be defined in some way. You have to make sure when the enthalpy of formation for CO2 is in a table, and for methane it's in a table, and for, or let's say just pure carbon, pure O2, you have the reference enthalpies, and then you have the reference enthalpies of CO2. These three, they need to be consistent somehow to reflect that potential from the reactants to the products. Okay? They need to be defined in a way that the difference between them, I mean, if I convert carbon and O2 to CO2, that difference is really, what comes out. And so the way it's defined in the tables is that for each element, you need to define one reference, and then everything's fine. You can think of it like I said, it's not exactly what it is. You can think of it like I said earlier. Let's say you say carbon, hydrogen atom, hydrogen atom, they're both defined to have 0 enthalpy of formation, and then I can just stick them together to a methane, CH4, and then you measure the enthalpy of that and then take the difference. But it's easier to define reference enthalpies of these molecules because in this form is much easier to measure the enthalpy of these species. And so if you look at these tables, then typically hydrogen, oxygen molecule, and nitrogen molecule at 298.15, they would be equal to 0. Okay? And then solid carbon, because that's at this temperature, that's how you find carbon. Solid carbon, these are chosen to be 0, and then resulting from this, then you see here H2 and O2. If you have a system with H2 and O2 at 298, then the reference enthalpy is 0. And if I convert it then to H2O, then you see this here should be negative, and then this means I can convert this to thermal energy. Yes? Why is it 0? It's not 0, it's defined. It's just defined to be 0. I need to have I need to just define everything consistently. And so I need to get one, need to provide one reference value for each element. Okay? So I just say hydrogen molecule is 0, oxygen molecule is 0. It's not that they have the same energy. They don't. I just use that as a definition, and then everything else is consistent. Okay, so this is how you compute these values. This would be the CP. This would be the enthalpy. And you see these are given here as function as temperature polynomials. This is the entropy temperature polynomials. And these polynomials here are given like this. You can find these on the internet. You'll find these thermo data tables. Typically, they have these, how many coefficients? I can't remember. Like 2, 4, 6, 12, 14 or whatever coefficients, and they are usually in 2 temperature ranges, one for lower temperature, one for higher temperature, just to make it more accurate. And if you take this here for hydrogen and you plug in all these numbers in this polynomial, and you do it for 298 Kelvin, you should try to do this, then it should be 0. Okay? Right, so maybe we'll stop here, and then after the break, we'll talk about these first law, second law aspects.